Greetings, physicists. This video will be about solving Ohm's law problems, and also we'll do some resistivity in this video as well. So we've got a light bulb. This is a standard 100-watt bulb apparently, right there. And they give us a current, and they give us a time that we're going to leave it on, and we're just looking for how much charge flows through. Now this is an example of a problem that gives you some extra information. And we'll see that when we go to our equations, because we have an equation that has time in it and current, and that's this equation. Current is defined as the change in charge, or the amount of charge that flows through the wire per unit time. Well, that means that this value is completely irrelevant. We don't need the wattage here because we have both of the current and the time. Now an ampere, you should know an ampere is the same as a coulomb per second. So we're going to have to change minutes. So when we plug stuff in, we know we have 0.83 coulombs per second. Oh, wait, hold on. I did that wrong. We're going to rearrange this equation by multiplying by delta t. Cancel. And so the Q is what we're looking for, right? How much charge flows. There we go. So the charge that flows through will be equal to the current times the time. So the current is 0.83 coulombs per second times the time, which is going to be 60 seconds. And now the seconds will actually cancel. That's good. So 60 times 0.83, which I think is a 12th. Oh no, it's 0.083. Let's find out. If I knew what fraction that was off the top of my head, that would be good. It's probably like 5/6. If it's 5/6, this is going to be about 500 seconds. So 0.83, or sorry, 50 seconds, not 500. Haha. Times 60. Yeah, 49.8. So this does round to 50 seconds. Okay. Not 50 seconds, 50 coulombs. Which is quite a lot of charge to flow through a wire. Although it's over the course of a minute, so it's not that bad. For instance, lightning bolts transfer, coulombs of charge, but they do it over, milliseconds. So they have quite a bit more power output. All right, on we go to the next one. So when you look at a light bulb, there's the glass outer part that doesn't really do anything other than keep the metal parts away from you. And then inside there's this like metal piece, and that's the part that actually is getting hot, and when it gets hot, it sends out light. And so, and that's tungsten. It's a big piece of tungsten, or a very thin piece of tungsten, actually. So we've given something. We're connecting this to a 120 volt outlet. It's a 60-watt bulb. It's carrying a current of 0.5 amp. What is the resistance of the filament? Again, I believe there's information here we don't need, right? Our equation, our Ohm's law equation, is V equals IR. And we're looking for resistance. We don't need power. We just don't. I think you can do this with power. There are ways to rearrange this equation to have power in there, but for now, who cares? The voltage divided by, so we'll divide by I. And the resistance then will be the voltage divided by the current. So it's 120 volts divided by 0.5 amp. Well, 120 divided by 0.5 is the same as multiplying by 2, so that's 240 ohms. That's nice. They gave us easy numbers. Although I think those are true, actually, numbers as well, so you could use that at home with your 60-watt bulbs. Now, this problem kind of uses that information that we just calculated. 60-watt bulb has this resistance. And once it gets up to its operating temperature, so that resistance is actually going to change depending on how hot the wire is, but once it gets fairly lit up, then that's going to be relatively constant. This is why, by the way, when you turn on the lights, they might look dim at the beginning, and then as they heat up, they tend to change their brightness. Is because their operating resistance is changing as it gets up to maximum temperature. All right, we know this. We know a resistivity. Okay, so that's rho. That's that weird P-looking thing. Rho is 5 times 10 to the minus 7 ohm meters. We know R is 240 ohms for the bulb. And again, I don't think we need power. So in this case, they're using, every single problem has had some wattage bulb in there, and it's almost like the 60 watts is just the name of the bulb, not a measurement that we really care about. We also have the diameter, which is, I guess we could say D equal to 0.040 millimeters. Now, let's look at our equation. Resistance was equal to rho L over A, and L is what they're asking for. Yes, how long would the filament be? And we have rho, and we have R, and then A, we have to deal with A. Well, if you look at a wire from the side, the diameter is this. It's of a circle. And so we're just going to have to take that times pi is going to be equal to the area. And that's how we'll deal with this. So coming down here, let's rearrange this equation to solve for L. L will be equal to resistance times area divided by rho. Also, we have to make sure we change this into meters. So right now, it's a times 10 to the minus 2, and a milli is a times 10 to the minus 3, so that's going to be a 10 to the minus 5. So, and that's going to work out nicely, I think. So the resistance on top is 240. Ohms are good. We like that unit. The rho, actually the rho's on bottom. Hang on. The area on top is going to be 0.0. Oh, nope, I already decided I was going to do it in powers of 10, so it's going to be 4.0 times 10 to the minus 5 meters. And then on bottom, the rho is 5 actually that would be meters squared, wouldn't it? I did the circumference. Silly. No, it should be pi r squared. So it's, let's go back to this. Let's put through that. The area is going to be equal to 4 times 10 to the minus 5 squared times pi squared times pi. Okay. All right, and we go back down here. 5 times 10 to the minus 7. And you know how I figured that out is I was looking at it and going, wait, this is ohms. If this was just meters and this was ohm meters, the meters wouldn't cancel. But if the meters on top are squared, then I would wind up with an answer that's in meters. Okay. Whew. All right, let's simplify that a little before I throw it at my calculator. I'm going to have equal to 240 on top times 4 squared is 16 times 10 to the minus 5 squared is 10 to the minus 10. On bottom, that's a 5 and a 10 to the minus 7. Well, look at that. I'm going to cancel minus 7 tens and get minus 3 left on top. 240 over 5, if I double top and bottom, is actually 480 over 10, so that's 48 if I cancel at 0. 48 times 16 times 10 to the minus 3. Let's see what the calculator says. 48 times 16 is 768. So 768, 10 to the minus 3. Well, that's just move the decimal. 1, 2, 3. So 0.768 meters, or about 77 centimeters. Because we're rounding. This is a 2 sig fig problem, yeah? Yeah, that's a 2 sig fig problem. So 77 centimeters long. I mean, that's pretty long. It's not a full meter, but if you think about it, that's the length of the wire that fits inside that bulb. So it's actually coiled around itself quite a bit. That's why you see that shape to light bulbs, because they're trying to cram 3/4 of a meter worth of tungsten wire into that little bulb, which is, 10 centimeters wide, maybe less than that. So there you go. Let's keep going. 15 ohm resistor and a 1.5 volt battery. I'm going to draw this for myself. Now we have a circuit. So a battery here connected to a resistor like so. And if I'm labeling them, that is 1.5 volts and that is 15 ohms. The positive is the big terminal, the negative is the small terminal. And it says draw a graph, and things on the graph are going to be a potential difference and distance traveled through the circuit. Distance traveled being independent variable, right? How does potential depend on distance traveled, right? A function of. So when I draw my graph, actually let me give myself some more room here. My vertical axis will be potential difference in volts, and my horizontal axis will be distance traveled, which is odd because we don't think of having a distance traveled equation. So what I'm going to do instead, if we look at this, it says starting at 0 volts at the negative terminal. So we're pretending that when we start here, we're at a potential difference of 0, or at an absolute potential of 0. Well, let's think about this. Current goes from positive to negative in a circuit like this. So where am I going? Well, from negative, I'm going to the positive terminal. From the positive terminal, I'm going through a bare wire up to the resistor. Then I go across the resistor to here, and then I go through and I end up back at the negative terminal. So that's the distance I travel. So what I'm going to do on this graph is really just label those 4 regions. Here is the negative terminal. I travel from the negative terminal to the positive terminal. I travel from the positive terminal through a bare wire to the beginning of, I guess this would be the resistor here, and then I travel across the resistor to the point after the resistor, and then from there I travel back to the negative terminal. And that is how I complete this circuit. Well, it says I start at 0 volts. So that's going to be a 0 right there. And I travel from there to the positive end of the battery. I'm going like this, all right? And the positive terminal is 1.5, so let's mark that. That's 1.5 volts. So that's going to be that distance there. And I'll just assume that's a constant increase. From there, I go over here to where so that's like this traveling here, up to the resistor. Now the bare wire does have some resistance, so there is some potential loss, but we usually don't consider it in these problems because it's so much less than the resistor itself. So let's assume that going through a bare wire we don't lose any potential, and so we just have a flat line there. When I go across the resistor, however, I'm going to end up at this point, and again, the last part of the journey is going to be this, which goes back to the negative terminal, and it's through bare wire. So we're going to assume that I'm going to have to end at 0, and that this part of the wire is also at 0 because we don't really lose any potential there. So that tells me that from here across the resistor, I have to get down to 0. Okay, so that's our graph. Not a really conventional graph, but that's what they asked for. What is the current in the circuit? Well, the current in the circuit can be done with Ohm's law. V equals IR. If I do that, I have to divide by R, so I'm going to get I equal to V divided by R. And they made the numbers really easy, right? That's 1.5 volts on top divided by 15 ohms, so a tenth. 0.10 amps. 2 sig figs. Yeah, makes sense. The second part was easier than the first. All right, I think this is the last one. We have a car, the battery, the electromotive force. When you see electromotive force, pretty much the same as voltage as far as this level is concerned. Of 12 volts. And that's pretty standard for car batteries. When the car's starter motor is running, not the motor that turns the wheels, but the motor that ignites the gas, the battery current is this many amps. What power does the battery supply? Okay. Let's see what we got here. We have a current of 320 amps. We have a voltage of 12 volts. And we're looking for power. Now we do want power, okay? Everybody wants a little power, right? Power equation for an electric circuit is power equals VI. Oh, so this is super easy. 12 volts times 320 amps. Okay. And I get 3840 watts. Now these are both 2 sig figs, so I'm going to just kind of round that to 3800 watts. Right there. Quite a lot of watts. I'm curious what that is in horsepower. What is a horsepower? Like 150 or something? No, 57. I think it's like 57. Horsepower to watts. 1 horse. No, it's like 700. I think there's a 7 in there. Like 750. About 750 watts. So if I want to do that, I have to do 38 divided by 750. Okay. 3800 divided by. Sorry, this is just for your edification. It's like 5 horsepower. So while this looks like a lot of watts, this wouldn't get your car very far. Because it's just used to ignite the gasoline. Once the gasoline is ignited, then the motor, the other motor, the one that turns your wheels, that probably operates at a much bigger horsepower. But that's not an electric motor, that's a chemical motor. Although, depending on your car, you could get an electric car with more horsepower. But this is obviously talking about a car with a starter in it. Okay, hopefully this helps you solve current and resistance problems.